Hello YouTube, De-bodgery here, aka Richard Gumfaw on Facebook. Welcome to EV Components Review. If you see anything here that you like, feel free to subscribe, like my videos, hit the notification bell, leave comments in the video, stuff like that. All that stuff helps my channel to grow, and so appreciate it if you do. Anyway, we are looking at the power stage for a Talaria controller. The MOSFETs are pretty good, but other details here are not really that great. So anyway, yes, these are magnet chip MOSFETs, as you can see right there, and that's a good brand. And they are 10N025s, and that is a 2.5 milliohm, 100 volt, 240 amp MOSFET. So as far as current capability here, each one of these things can max out at 240 amps. Well, yeah, that's going to be a decently powerful MOSFET, and their gate resistance is fairly low, so that's also really good. They're not going to generate a lot of heat, and Magnet Chips is a great brand, so that's also really good. Definitely like those aspects of this controller. These MOSFETs are going to be pretty darn good. They do take a fair bit of gate drive current, which is why it is that we saw up on the power stage that we had, those extra MOSFETs and things to kind of boost up current for the MOSFET gates, but at the same time, they all have a gate current limiting resistor, like you see here and here and here. But that brings up another interesting thing. So you'll notice that there's also, like here and here, there's a small capacitor, and this is for high frequency gate filtering. But like on this one here, there's not one there. And in fact, I don't know what this resistor does on here. And there is the, right there, that one. Yeah, and that was doing something else. And then like this resistor and that one, that's got something else to do. That's nothing to do with gate filtering. But yeah, it's odd that, they all have the gate drive current limiting resistor. But then this one's also got the capacitor. And then this one doesn't have it at all. And again, you can see that same stuff is here. Here's your great gate drive. There's this other resistor, and here's that high-frequency filter cap. But, yeah, it's not one here for that MOSFET. And if I look over this next phase, you'll see this again. Yeah, see this one here, this MOSFET? It doesn't have the capacitor. Or, I'm sorry, yes, it does. It's that one right there. Yeah, it only has the resistor for gate current, but it doesn't have the capacitor. So, kind of odd. Anyway, yeah, and it's not like it's consistent either. These ones here, you've got 3 in a row, and then this last one on the end, which is the last MOSFET in that phase, that's the one that doesn't have that capacitor in it. Whereas this one here, here's your 4 MOSFETs for this phase. So you've got one, you don't have one, you got one, and you don't have one. Yeah. And then we go over to this one right here, and it's... you got one, you don't have one, you used to have one, except for it ripped up with the potting, and you don't have one here. So it's weird. I don't know what they were doing there. To me, that would make some odd things go on in these phases. There used to be 4 little ceramic caps right there, but they tore up with the potting, and they're for that high frequency battery bus filtering. So this is battery minus, and this trace right here, that's battery plus. So that's what they were for. And if I go down here, yeah, one of the 4 survived depotting. The other one's ripped up with that rock hard potting. It heated up, get it really nice and warm, like 250 degrees Fahrenheit. Not enough that would harm any of the electronics, but hot enough to get the potting soft. And then I would start peeling it up, and it would still rip up parts. Yeah, you can see another capacitor or whatever. Yeah, capacitor that came up with it. Anyway, yeah, these little ceramic caps, they're inadequate, because this right here, this is battery plus, and this down here is battery minus, and that's your high-frequency filtering. Yeah, it's kind of an odd setup that they use such little fiddly caps like this, but then again, KO did that as well. They used, small caps, and not very many of them, to do all of your high-frequency filtering for something that needed a lot more. So right here, this is your battery minus stud, and this one is that one that I showed on the logic board. That's just that standalone battery minus, and this is the other one that goes up to that whole battery minus plane. anyway, you can see that it's reinforced with some solder. Yeah, kind of weird. Not putting copper down, but then again, as far as battery minus is concerned, it's a pretty wide piece of copper across here, so it's probably enough for this job. And then they beefed it up a little bit with some circuit traces, which seems sort of strange. All this grunge that's on here, I don't know what caused that. That is not from me. Maybe that was something leaching out of the potting. Your guess is good as mine. Anyway, it's still all here. Oh, check that out. So, that's a broken trace right there, it looks like. Yeah, oh wait, maybe not. I wonder what that was. Yeah, okay. Yeah, it looks like permanent marker on here. Oh, hey. Does it? Yeah, it does. That's an ARA Talaria, maybe? ARIA Talaria? I don't know. Sure, that's what that says. So somebody wrote that on permanent marker in here. Let's see what else to look at here. Yeah. So let's talk about something slightly different that I have mentioned before. And there used to be a stud right here. In fact, here's that stud that was soldered right there. Anyway, this is a fairly common problem with metal core circuit boards. So this white area here, this is a layer of ceramic bonded to the aluminum. And ceramic makes a pretty good thermal conductor, and it also makes a pretty good electrical insulator. So yeah, it's a common thing that's used on metal core printed circuit boards to isolate the aluminum back from the circuit traces on the top. The problem with it, though, as you can see here, and as you can see here, circuit traces don't bond to it particularly well. So if you're going to put something that's got to take some stresses, you need to make it pretty big. And yeah, you can kind of see the circle right there where that stud used to be soldered down. And when I was depotting this thing, the potting was pretty soft, but it still put a lot of stress right there, and it lifted up the copper, as you can see all over the place. And that was from potting. That wasn't even from like turning a screw. Like what you'd see with, like, say, a KO Pro controller. But again, this is exactly what would happen with a KO controller, because it's got a very, very similar amount of surface area on the circuit trace, and you crank on that stuff too much, and it's going to tear up and destroy itself like this. So yeah, this is no bueno. All the way around. Yeah, I've mentioned that KO shouldn't do this, and here they are doing it in Talaria too. In fact, Sauron does it as well. And yeah, this isn't very good. Yeah. Another thing here is you can see that this is, by the way, this is your phase bus right through here, all this area. Yeah, here's your MOSFET legs going into the phase bus, and here's the other side of the other MOSFETs, part of their phase bus. And all they've done is use the copper trace and then sort of kind of reinforced it with some solder. I don't even know why they bothered. Yeah. There's this invention, it's called copper reinforcing. Put that in here. Yeah, put that in here. And then you could also completely cover this area, and then when you solder that stud down there, now it's got some reinforcing, and it wouldn't tear up all of this stuff. Because, well, its stresses would be distributed around a whole entire piece of reinforcing copper, rather than just, on the circuit traces, which don't bond particularly well. Yeah, this is a problem that everybody who does MCPCBs has to work with. And it's basically, make sure that you give, there's a loose capacitor, make sure that your circuit traces around studs and things have plenty of reinforcing so that this doesn't happen. Right here you can see the connector pins, the little connector header, or pin header rather, for getting gate signals and things down to here. Right here, so you can see those 4 little ceramic capacitors. So that is your high frequency filtering. Its location is fine. I don't have a problem with that. It's just how fiddly small they are. There's not much capacitance here. I haven't measured it. I could pull out my LCR meter and find out, but yeah, there's not going to be very much capacitance, these 4 little dinky chips. So yeah, I'm going to say that probably the DC bus right here has probably got some high frequency noise on it. And you can see that same thing again. Like this MOSFET right here, it's got a resistor on the gate, whereas like this one here had the MOSFET, has a gate resistor, and it's got this capacitor on there as well. Yeah, and there's this other resistor that's on there for some kind of gate high frequency filtering. And then you come over here and, well, it's completely different. You just kind of have one capacitor and one resistor. And yeah, you can see this one is all torn up as well. Yeah, that's going to be super good. Yeah, that's going to be super good. Yeah, there's the gate. And then you come over here, and now it's got that 3 set again. It's inconsistent. So right here and here, these are your 2 pin headers for getting gate signals from up above to down here. With the exception of 2 of those pins go to that little guy right there. And this is the one and only thermistor on this board for temperature sensing. And it's more or less kind of center in the board. Yeah, just one. And again, you know, here is your pseudo, sort of, kind of reinforced copper with a little bit of solder. Yeah, which really ought to have copper on it, not just that. All right, let's move all the way over here. Yeah, so that's battery plus. Yeah, you can definitely see all the ceramic underneath it, and it's mostly pulled up. Yeah, this is exactly the same problem that you'll have in the KO controllers. You crank on those screws very much, and you will literally rip them up. With these ones, all these ridges on here, and this being hard potted like it is, these are actually much less likely to tear up just because they can't turn when you crank screws on them, because they're going to be all embedded in potting and hard potting. Whereas like in the KO controllers, well, that's not the case. So yeah, all the stress on these studs is all going right down to here, and then they basically do this and then rip off. And I already know for a fact that that's happened. Yeah, I've seen it. So yeah, not really ideal. The battery plus bus down here is basically this width right here. And you can see it back up underneath here. Yeah, you can kind of see right there underneath the MOSFET all the way up to here. So that's your battery plus bus. And of course that's reinforced by the underside of the logic board. So not exactly ideal. If they would have just shifted these MOSFETs down, like, I don't know, you know, a quarter of an inch or something, they could have taken copper all the way across here, all the way across the top, and reinforced all that stuff. And they didn't. They kind of cheaped it out with this, you know, bit of solder, kind of pseudo half reinforcing things. I don't ever like seeing this kind of stuff. This is always crappy. You know, this is cheap. Yeah, and you can see that this stud is also loose. That's the 3rd phase bus right through there. Yeah, that's all torn up as well. Yeah, once this starts happening, you're going to be buying a new power stage, and that's pretty much all there is to it, because this only gets worse from here. Yeah, the printed circuit board part, that's fine. It's how you use it. That's the problem. And, well, these are at least reinforced with hard potting. But in other controllers, they are not. So, yeah, that's super cool. Anyway, I think that's probably everything I want to show you in here. Yeah, I think so. So, hope to help some folks out. Hope you enjoyed that teardown of a Talaria power stage. Next up, I will be doing the same thing for Suron. You know, getting in with my macro lens and getting a nice close look at its logic board and power stage, just like we've done here.